Okay, so we've got the solution to our differential equation for the Green's function. What we want to do now is we want to perform this integral. We're going to want to integrate over P naught. And we're going to integrate over P naught. So integrate over P naught using the residue theorem. Now, if you know the residue theorem, you can just skip this bit. But I'm just going to tell you what the residue theorem is. If you've never seen the residue theorem proved, or maybe you never got the proof the first time, when we're back together in class, you can ask me, and I'll happily derive it for you on the blackboard. But let me just state what the residue theorem is. So the residue theorem, it's a theorem from complex analysis. And to state it, let's imagine you have some complex function. You have a function. It's a function of the complex variable z, and it is singular at z1, z2, and all the way up to zn. So what does this mean to say it's singular at these points? Well, our function f of z is an analytic function. It's a complex differentiable function. That means it obeys the Cauchy-Riemann equations. But at these singular points, z1, z2, at these points, it does not obey the Cauchy-Riemann equations. That's what we mean by saying that it is singular. Near each singularity, so near each singularity, there's a theorem that tells us f of z admits a Laurent expansion. And what does this look like? So I should stress this is an expansion near each singularity. The expansion looks like this. F of z looks like it's a sum over some integer n going from minus infinity to plus infinity. Then we've got some coefficient, some number zn, and we've got z minus zi to the n. So here I am expanding close to singularity at z is equal to zi. Now, what you can see is when I let z go to zi, that's going to 0. So all of the negative n's give me an infinite contribution to the function. So the function is blowing up at z is equal to zi because of all of the negative n terms, the terms where n is negative. If your function has no terms with n negative, so if the cn's were 0 whenever n is negative, then the function will be regular at that point. So it's singular because of those terms with negative n. One of these coefficients, c minus 1, plays a very special role. C minus 1 is called the residue of f of z at z is equal to zi. So the residue is defined at the singular point using the Laurent expansion of the function at that singular point. Now let's imagine that we want to perform the following integral. We're going to integrate our function f of z dz, and we're going to integrate it over some path c. So let me draw on c. So perhaps this could be c. That's c. And there's a few important properties that c has. First of all, c is closed. So it's a closed path. That path has no start point and no end point. The other thing that's important is it goes counterclockwise around the singularities. Okay, so this path C is circling a number of the singularities. It's going counterclockwise around those singularities. So those are the two important things about C. It's closed and it goes counterclockwise around the singularities. What the residue theorem tells us is the answer for this integral is 2 pi I times by the sum of the residues of the singularities inside C. Good. So that's the residue theorem. And we're going to use this. Now, this might be the first time that you're seeing the residue theorem. So I just want to give you one example of using the residue theorem. I want to calculate an integral. That's so easy we can do it by hand. And then I want to redo the integral using the residue theorem, just so that you get some experience with using the residue theorem. So the integral that I want to perform, it's an integral from minus infinity to infinity of dx over 1 plus x squared. Well, I think that you guys all know how to do that integral. This is just the arctan of x. So this is the arctan of x evaluated between infinity and minus infinity. The arctan of infinity is pi by 2 minus the arctan of minus infinity is minus pi by 2. So we'll end up getting an answer of pi for this integral. So that's nice. This is a nice, easy integral to do. Now let's try to repeat this integral, but this time we'll do it using the residue theorem. Good. So let's start off again with I. It's an integral from minus infinity to infinity, dx over 1 plus x squared. Now, we know from the residue theorem that all of the contribution comes from singularities. So where are the singularities of this integrand? Well, we've got an integral from minus infinity to infinity. We can write this as dx over x plus I times by x minus I. So what you can see is this integrand does indeed have singularities. It's got singularities at plus I and minus I. So let's just draw a picture of that. So here's the complex plane. Okay, I should say that I will always denote the complex plane by putting this little symbol with the Z in the right-hand corner. Okay, so that's always how I will denote the complex plane. And then where do the singularities sit? Well, there's one singularity at plus I, and there's another singularity at minus I. So there'll be residues at those 2 points. Good. Then what path are we integrating along? Well, we're integrating along this path. So let's draw it in blue. So that's the path that we're integrating along. Okay. Our first obstacle in applying the residue theorem is that we don't have a closed path. So the first thing that we need to do is close the integration path. So let's see how we're going to do that. So close the integration path. This will pretty much always be the first step that you'll do when you're applying the residue theorem. And you can choose to close it in whatever way you wish. So let's imagine that we decide that we're going to close it by adding this green segment of the path over here. Okay? Now, you can't just add a bit to your path without changing the integral. So what I'd like to do now is I'm going to try to integrate along that green piece of the path and see what contribution does this give to the integral. So let's say along the green path, what do we have? Well, we can write that x is equal to r e to the I theta. We must take r to infinity. Okay, so we must take that limit. And also theta goes from 0 to pi. Okay, So if we take r to infinity and we go theta from 0 to pi, we're going to go along that green path. From that form for x, we can write down what is dx. Well, r is just some constant. It doesn't depend on theta. So the r just sits out there. We've got the e to the I theta, and then we will have I d theta. So if we now look at the integral along the green path, so let's say GP for green path, then we know we must take the limit that r goes to infinity, okay? And then we've got dx, which is r e to the I theta, I d theta, over 1 plus r squared e to the 2I theta. Now, in taking that limit that r goes to infinity, you know, r is going to become massive. So in that denominator, that 1 plus r squared e to the 2I theta, forget the 1. That's going to be completely negligible. So we're just going to drop the 1. Then we'll have an r over r squared. So we've got a 1 over r. We've got an integral e to the I theta of I d theta over e to the 2I theta. And we should be integrating over theta from 0 to pi. Well, that integral over theta, whatever it is some finite number. So we've got some finite number divided by r, and we're taking the limit that r goes to infinity. So we've got the limit that r goes to infinity of some finite number over r. Well, that's obviously 0. So actually, the green path contributes nothing. So instead of integrating, instead of performing the integral in I over the blue path, we can just as easily do the integral over this new path, C. And because the contribution from the path at infinity vanished, what we just checked, this is still an equality. So this is dx over x plus I, x minus I. And this is great because now we can try to apply the residue theorem because we're integrating along a closed path and we are going counterclockwise around the singularity. We'll finish this off in a minute.